This lecture is in continuation to our previous lecture where we are studying about line spectrum of hydrogen atoms. So if you have not viewed that lecture, you can go ahead and look at that lecture in order to understand this, right? Because we have already almost done everything on line spectrum in that lecture, right? So here we would be talking much about these lines, right? This group of lines that we see in the line spectrum of the group of lines that we see in the line spectrum of hydrogen atom. Right. I'll just okay. This is the kind of spectrum of line spectrum of hydrogen atom that we get, and it consists of group of lines, right? Group of closely spaced lines, and these lines are divided into 5 series, right? These group of lines are divided into 5 series. This is your Lyman, right? This is your Balmer, this is your Paschem, this is your Brakett, and this is your Pfund series, right? These are named after the name of their discoverers. Like Lyman discovered Lyman series, which is a group of closely spaced lines, and every line in the spectrum corresponds to a radiation of specific wavelength or frequency, right? Similarly, so we say that although an atom of hydrogen contains only one electron, I have discussed this in previous lecture also, right? So the subject would be the simultaneous appearance of large number of lines in the hydrogen spectrum. These are large number of lines in the spectrum of hydrogen atom. So it's simultaneous appearance of large number of lines in hydrogen spectrum. Right. Why do you see large number of lines? Although an atom of hydrogen, right, it contains only one electron, it has only one shell, right, it has only one electron, right? So why do we see so many lines in the line spectrum of hydrogen atoms? Like I said in the previous lecture, any sample of hydrogen taken in this discharge tube contains many molecules of hydrogen atom. So when these molecules, right, will absorb energy, right, when it will absorb energy, it will break into hydrogen atoms, right? And these hydrogen atoms will absorb different amount of energies, right? And their electrons, when they will absorb energy, so this electron will move to a higher energy state. Since I said that different atoms will absorb different amounts of energy, so electrons will get excited to different energy levels, right? These hydrogen atoms will absorb different amount of energy, due to which electrons will move to different energy states. Due to this, electrons will move to different energy states, right? So let's just write it like this. Maybe say these represents the different energy states, right? This is one energy state, this is another, right? This is another, then there is one more, then here, right? These are like, let these lines represent different energy states. These lines will represent different energy state. N is equals to 1, N is equals to 2, N is equals to 3, N is equals to 4, N is equals to 5, right? N is equals to 6, N is equals to 7, N is equals to 8. right? Now these electrons, right, which are excited when electric discharge is passed, when these hydrogen atoms, right, absorb energy, they would be excited to different energy levels, right? When they will be excited to different energy levels, some will move to n is equals to 2, some will move to 3, 4, 5, 6, 7, right? They will move to different energy levels. It's like these are the energy levels, right, of an atom. So these electrons will move to different energy levels, right? We know that when electrons will move to different energy levels, these energy levels are short-lived. The electrons will stay in higher excited energy levels for a short period of time, and after that it will come back to its ground state, or it will fall back to different energy levels, right? Suppose electron, right, in this, suppose an atom absorbs more energy and it excited to n is equals to 8 level, right? So it will return from n is equals to 8 level to, say, here n is equals to 1, right? Then some electrons will move from n is equals to 7 to n is equals to 1, some will move from 6 to 1, some will move from 5 to 1, right? Similarly, some electrons will move from different energy states to n is equals to 2, like here, right? Similarly, some other will move to n is equals to 3, some will move to n is equals to 4, right? So if you look at this, the formula was delta E is equals to RH, right, 1 upon Ni square minus Nf square, right? So if you put, suppose for this transition level, N8 is your initial and final is your Ni, Nf is your N1, final is your N1. For this transition from 8 to 1, initial is your 8, final is your 1. So if you put these value, you will get radiation of specific wavelength, and from there you can find frequency. Delta E is equals to h nu. From this relation you can find frequency and wavelength, right? So as electrons are transitioning from different energy levels, right, so when they will transition from different energy levels, they will emit radiations of different wavelengths or frequencies, right? So this would be different radiation, this would be different radiation, because if you will see, from to n is equals to 1 level, right, electrons from different energy levels are falling back to n is equals to 1, right? So here, here initial state is changing, right? It's 8, 7, 6, 5, right? And final state is same, it's n is equals to 1. So when electrons from different states, right, will fall back to n is equals to 1, right, we get radiations of different wavelength based on this formula, right? And corresponding to every wavelength you have a line in the hydrogen spectrum, right? Similarly, okay, to this series of lines, right, that we see in the spectrum, when electrons from different energy levels move to n is equals to 1 level, we call it as Lyman series, right? Similarly, when electron from different energy levels will fall back to n is equals to 2, right, the series of lines is this is your Lyman, right, which is as a result of falling back to n is equals to 1 level. Similarly, when electrons from different energy levels will fall back to n is equals to 2, what you get is a Balmer series, right? Similarly, when electrons from different energy levels will fall back to n is equals to 3, what you get is a Paschem series, and this is your Balmer series, right? Similarly, this series right, that you get when electrons from different energy levels, right, will move to n is equals to c, right, n is equals to 4, I'm sorry, what you get is a Brakett series, right. Similarly, the other one, the last one, is your Pfund series. When different energy levels, when electrons from different energy levels will fall back to level n is equals to 5, right, the radiations emitted, right, will consist of closely spaced lines, which is known as Pfund series, right here, which is as a result of falling back from n is equals to n is equals to 5 or fifth energy level. Here n is equals to 4, when electrons from different levels will fall to n is equals to 4 energy level, right. So you see these lines of different closely spaced lines, right, in the spectrum of hydrogen atom, when electrons from different energy levels will fall back to specific level, and these levels are named after the name of their discoverers, right. So that is this series, the Lyman, this was discovered by scientist Lyman, so we call it a Lyman series. This was discovered by Balmer, this is your Balmer series, right. And one important thing is, since we know that these lines corresponds to radiations of different wavelength, right, and if you see these radiations where they fall in the electromagnetic spectrum, you will see that only Balmer series will fall in visible region, right, Lyman series will fall in UV region, ultraviolet region, and rest of the three, these three will fall in infrared region, right, of the electromagnetic spectrum, right. This is important, right. So that is why you see lines of different wavelengths, right. I'll just quickly repeat, right, the different excited electrons, right, adopt these excited electrons, right, excited electrons that move to second, third, fourth, fifth, up to 8th energy levels, right. They different electrons adopt different routes to return to various lower energy levels. What these electrons are doing, they are returning to lower energy levels from higher energy levels, and when electron will return to lower energy level from higher energy level, they will emit radiation of different wavelengths, right. So as a result, they emit different amount of energies, right, which can be seen from this formula, right. When electrons from n is equals to 8 will move to 1, you can find the energy of the radiation or frequency, right, which will correspond to a line in the spectrum. Similarly, when electrons from different energy levels will move, right, to this second energy level, right, the series of lines is known as Balmer series, right, and the energy can be taken as by NF is equals to 2 and NI is equals to 8, right, or 7, right. So when from different energy levels, right, electrons will return to n is equals to 2, right, what we get is a Balmer series which lies in visible region. Similarly, when electrons from different energy levels, right, say from this when electrons from different energy levels will fall to n is equals to 3, right, say from 4, 5, 6, 7, when all these electrons from different energy state fall to n is equals to 3, right, what you get is a series of lines, right, which consist of radiations of different energies, right, or frequencies, right, and you call this series as Paschem series, right. This is the reason that you see too many lines in the spectrum. The reason is simple for too many lines, that electrons, right, in the hydrogen atoms, right, are excited to different energy levels. So when they return to lower energy levels, right, they adopt different paths, right. So when they return to lower energy levels, right, they will emit radiation of different wavelength or frequency. Why? Because based on this formula, if you look at this, the Ni and Nf would be different. So energy and radiation would be different. This is the mathematical explanation, right? So when they return to a specific energy levels from different energy levels, you will see group of lines, right? And these group of lines are named after the name of their discoverers, right? And these, you can find this in which region of the electromagnetic spectrum these waves, right, these radiations fall. The Lyman series, the radiations, right, the lines, right, the lines corresponds to a specific radiation, right? So these radiations in Lyman series fall in UV region. Similarly, Balmer series is the only series that fall in visible region, and rest of them fall in infrared region, right? So I hope this is clear. Thanks.